State and prove Rodrigue's formula for a curve to a line of curvature. Now statement: the necessary and the sufficient condition that a curve on a surface to be a line of the curvature is that KdR plus dn equals to 0 at each point of its points. Now proof: necessary condition: let the curve be a line of the curvature on the surface R equals to RUV. The line of the curvature are given by L minus KE du plus M minus KF dV equals to 0, equation 1, and M minus KE into du plus N minus kg into dV equals to 0, equation 2, where K is one of the principal curvature. Now putting E equals to R1 square, F equals to R1 dot R2, and G equals to R2 square, L equals to minus N1 dot R1, M equals to minus N2 dot R1 equals to minus N1 dot R2, and N equals to minus N2 dot R2. In 1 and 2 we get minus N1 dot R1 minus K R1 square du plus minus N2 dot R1 minus K R1 dot R2 dV equals to 0, and minus N1 dot R2 minus K R1 dot R2 dV du plus minus N2 dot R2 minus K R2 square dV equals to 0, or N1 dot R1 plus K R1 square du plus N2 dot R1 plus K R1 dot R2 dV equals to 0, and N1 dot R2 plus K R1 dot R2 du plus N2 dot R2 plus K R2 square dV equals to 0, or N1 du plus N2 dV dot R1 plus K R1 du R2 dV dot R2 R1 equals to 0, and N1 du plus N2 dV dot R2 plus K R1 du plus R2 dV dot R2 equals to 0, or dn dot R1 plus K dr dot R1 equals to 0, or dn R2 plus K dr dot R2 equals to 0, because dn equals to del n over del u du plus del n over del v dv equals to N1 du plus N2 dV, and dr equals to del r over del u du plus del r over del v dv equals to R1 du plus R2 dV, or dn plus kdr dot R1 equals to 0, and dn plus kdr dot R2 equals to 0. This is equation 3 and equation 4. Since the vector dn plus KdR is a tangential to the surface. Therefore, the equation 3 and 4 will hold good only if dN plus KdR equals to 0. Hence, the condition is necessary. Now, sufficient condition KdR plus dN equals to 0 along the curve for some scalar function k. Then along that curve we have KdR plus dN dot R1 equals to 0 and KdR plus dN dot R2 equals to 0. Now, the reversing the step of the first part, we get the equation L minus K du plus M minus Kf dv equals to 0 and M minus Kf du plus N minus Kg dv equals to 0. Thus, the curve will be a line of the curvature if we show that the K is a normal curvature on the surface, since KdR plus dN equals to 0 or KdR equals to minus dN or K R1 du plus R2 dv equals to minus N1 du plus N2 dv. Taking the scalar product of both sides with R1 du plus R2 dv, we get K R1 du plus R2 dv dot R1 du plus R2 dv equals to minus N1 du plus N2 dv dot R1 du plus R2 dv, or K R1 du plus R2 dv square whole square equals to minus N1 du plus N2 dv dot R1 du plus R2 dv, or K equals to R1 square du square plus R2 2 R1 R2 du dv plus R2 square dv square equals to minus N1 dot R1 du square plus N1 dot R2 du dv plus N2 dot R1 du dv plus N2 dot R2 dv square, or K equals to E du square plus 2F du dv plus G dv square equals to L du square plus M 2M du dv plus N dv square, because M equals to minus N1 dot R2 equals to minus N2 dot R1, or K equals to L du square plus 2M du dv plus N dv square upon E du square plus 2F du dv plus G dv square, which shows that K is the normal curvature at the point of U and V in the direction of du dv. Hence, the direction of the each point of the curve is a principal direction, and thus the curve is a line of curvature on the surface.